Thanks, Brendan. So as Brendan said, my name is Lars. And over the last couple of months, Taylor and we made Git LFS dramatically faster. That wasn't an easy project, because we had to make changes in Git Core and in the Git LFS extension code. In the next 30 minutes or so, we will talk about some challenges that we met through this project. But first of all, let's look at the results of our improvement. Here in the upper terminal, you see the last Git version 2.10, and in the lower terminal, the current version 2.11. And now, we are going to check out a branch with 500 files in LFS. So we're going to git checkout. And as you can see, the new version is already done when the old version hasn't even started yet. So that's Git LFS at light speed. But why do we need Git LFS? Let's quickly recap how LFS works, and let's use this video file as an example for a large file. So first, let's look at a repository without LFS. And let's add a bunch of code, 1 megabyte, to our repository, and let's also add our large video file. So after this commit, our repository has a size of 101 megabyte. And then we change our mind, and we change the color of this video. And then we add this new version of the video to our repository, which will add another 100 megabytes to our repository. And we change our mind again, which means we would add yet another 100 megabytes to our repository. And here you can see this tiny repository with just one large file and only 3 commits has already grown to a size of 301 megabyte. Now you can imagine I work at AutoDesk, and we have repositories with thousands of large files and hundreds of developers. So you can imagine the repository size of these projects, they explode. OK, so now let's look at the very same situation, but with Git LFS enabled. So again, we add a bunch of code, and we add our large video file. But instead of adding the video file directly to the repository, it is uploaded to a large file storage server. And only a pointer is placed in our repository. The pointer points to the file on the server. And the pointer is tiny. And if we change our mind for the file and create a new version, then this new version is uploaded to the LFS server. And only the pointer file is changed slightly. And of course, this is also true if we change the file yet again. And all this might look a little bit complicated, but it really is not. For you as a user, you wouldn't see any difference. The code files and the large files, they look as if they are completely in Git. All the complexity is handled by Git LFS under the hood. So this is great, because when you want to clone this repository, you just have to transfer 1 megabyte of data, which is super fast. And if you check out the master branch, then Git and Git LFS is clever enough to figure out what large files need to be transferred. In our case here, we need to transfer the last version of the video, the red version. And then Git LFS will download it on the checkout. So that means, just in this tiny example, we already saved 60% of the bandwidth. And now you can imagine with large repository with thousands of large files and hundreds of versions, the savings are incredibly greater. And this is really what LFS achieves. But let's go back to our speed improvement contribution. So how did we make Git LFS so much faster? In order to understand that, we need to look at the Git checkout process. So this is our Git checkout process. And whenever Git finds a pointer file during the checkout process, it will take this pointer file and give it to a new Git LFS process. The Git LFS process will go off and download the file if necessary, and then it will give back the content of the file to Git. And then it will shut down. This entire process is called the Git clean smudge filter mechanism. And this process will happen or happens for each and every file in your repository. So that means if you have 1,000 LFS files in your repository, then this filter process is invoked 1,000 times. Well, process invocation is expensive, especially on Windows. And that's why This takes a long, long time. What did we do? Well, we changed the protocol that Git uses to talk to Git LFS. And we changed it in a way so that Git, on the first pointer file, starts the Git LF process, and then Git uses this LFS process for every subsequent pointer file. And that makes it so much faster. All right, in the remainder of this talk, I will focus on the Git contribution process. I made some changes. I implemented the protocol in Git. That was interesting. But what was even more interesting is really the contribution process in Git, because that differs a little bit from the contribution process that you know from most other open source projects. And afterwards, Taylor will talk about some design decisions that he made while implementing the protocol in Git LFS. All right, so now, how do you contribute a change to Git? Well, Git is developed on a mailing list. That means all the changes, all the patches are sent to the mailing list, and all the reviews happen on the mailing list as well. What do you do if you have an idea for a contribution to Git? Well, the first thing that you need to do is you need to subscribe to the mailing list in order to get all these emails. And I recommend to set up a filter for your inbox, because you will get quite a number of emails every day. And the next thing you should do is you should search for your idea in the Git mailing list archive, because it's likely that your idea was discussed already, and you should read about all these previous discussions. If you can't find your idea, well, then it's time to write an RFC, a request for comment. Why is it necessary? Well, Git is an open source project, so that means you can't force a change into Git. You need to present your idea, and you need to convince the community that your idea is a good idea, and then they might accept it. A pretty convincing argument in the Git community is performance. So if you can measure performance and you can show your idea makes Git such and such faster, then do that. That's good. After you send your RFC, a discussion might start on the mailing list. And you should follow a couple of rules to play along nicely with the Git forks. So one rule is they really like inline replies or bottom replies. Don't make top postings, because they are frowned upon. And also, configure your email editor to send text-only emails. HTML emails are frowned upon as well. OK, at this point, you have discussed your idea, and you have a pretty good idea about the things that you want to do. So you can start working on your feature. Usually, when you implement a feature, you would start from the Git master branch. If you fix an existing feature, then you would start from the main branch. And then you implement your feature, and the Git guys, they are pretty picky about their coding style. So you want to read the coding guidelines and write your code with these in mind. But don't stop there. You should also write tests for your feature to prove that it works as expected. And last but not least, you should write documentation to explain how your feature works to the end user. And then you commit your change. But when you write your commit message, then please be aware that the Git community cares deeply about commit messages. For them, they are as important as the code itself. And a good commit message has a number of properties. So first of all, it has a short one-line description. Sometimes the Git folks prefix their commit messages with a single word that identifies the area of where the code change was made. Second, there should be a paragraph that explains the problem that you want to solve with this commit. Third, you should explain your solution. And you should not only explain your solution, you should also explain alternative solutions that you have considered but discarded. And you should also explain why you have discarded them. In general, a commit message should be self-contained. That means a reader shouldn't need any external resources to understand the content of your commit message. And last but not least, you should add your sign-off. You have to add your sign-off, actually. This certifies that you wrote the patch and that you have the right to pass it on to the open source community. As a pro tip here, use a spell checker for all that, because the Git community cares about spelling as well. So after we've made all these commits, you're not done yet. Because a mailing list has an interesting property. So whatever you send to this mailing list is there. You can't change it after the fact. And that's why you should make sure that your commits are in the best possible state. And the most obvious thing to do is, of course, you would build Git. And you should make sure Git builds clean on your machine. If you have a number of commits, that's called a Git series, then you should also make sure that each individual commit builds clean. And you can do that with the git rebase command that I've shown here. And then, of course, you need to run the tests and make sure all the tests pass. As a matter of fact, there are many different rules that you could follow here. Here's another one, for instance, to check that you don't have trailing white spaces with the git diff -- check command. You will learn about these rules over time on the mailing list. What you could also do is you could use a prepared patch script that I've written after my experience. And it has all these things that I've learned inside. In addition to local testing, I also recommend to enable Travis CI on your fork of Git. This way, you can make sure that your change builds cleanly on Mac, Linux, and different compilers. And it even checks that your documentation builds without error. So when your commits are in a perfect state, then you can use the git format patch command to transform your commits to patch files. And these patch files, they look interesting, and I want to go through their structure a little quick here. So they have an email header. Then they have the commit message that you have written in your commit. Then they have a section for additional explanations that you can use for your own. They have a section for the statistics about your change, your actual change, and your own Git version. And if you use my prepare patch script, then this will insert some additional information. For instance, it will insert the base commit that you've used to write your patches, and it will insert a link to your GitHub repository hosting your patches so that people that prefer reviewing stuff on GitHub can do that easily. All right, so when you have made these patch files, then you can send them to the mailing list with the git sendmail command. And you should also CC potential reviewers of your patch. How can you find them? Well, you would usually run git blame on the lines that you have changed to identify people that would be able to review your changes. And again, you could also use my prepare patch script, which would do that for you. And then you wait after you send the emails. And if you're lucky, then people will respond to your patches. And that's a very good thing, because these people, they care enough about your change to spend their time reviewing it. And that's great. And a review sometimes means that someone doesn't agree with you and criticizes your code. And what you should do is find agreement. Find a solution that works for them as well as for you. And when you find these solutions, then make notes. And then, of course, you update your commits with these solutions, and you also check your commits as thoroughly as I explained it earlier. And then you prepare the next round of your patch series. And here, the notes come into play. What I usually do is I take these notes to write a high-level description of the changes that I've made between the different versions. And that helps the reviewers to see what you've actually worked on. And my prepared patch script actually supports this kind of workflow, so you can add a number with the version of your patch series in order to generate the right emails. And then again, you send the patches to the mailing list. And you should see everyone who has reviewed your patches so that you can make sure that they get the updated version. So to recap that real quick, let's look at the entire contribution cycle. You start with an RFC, and then you send the first version of your patches. Hopefully you get reviews, And based on the reviews, you create a version 2 of your patch series. And then you get other reviews, and then you create yet another version, and so on and so on. Sometimes it takes up to 11 versions to get accepted. And when your change is accepted, then it will be merged to the next branch. It will sit on the next branch for a while so that to make sure you don't break it, and then it will be merged to the master branch. And when it's merged on the master branch, well, that's great, because that means it will be released with the next major version of Git. That's kind of the gist of it. You can learn more about the entire contribution process in the documentation section of the Git repository. The file submitting patches is the one you want to read there. OK, to wrap that up, so the filter protocol change that I made to Git, here are a few statistics about it. So I changed 1,628 lines in Git. It took 11 iterations to get accepted. It took 380 review emails that went back and forth. And it took 6 months of work. So the lesson here is don't give up. Git has a very thorough review process, and that's a good thing. Because Git is used by millions of people around the world, and you don't want to be the guy that breaks Git. So without further ado, now I want to hand over to Tyler. Hey.
Thank you. Hi, as Lars mentioned, my name is Taylor. I'm an infrastructure engineer at GitHub, where I work on Git LFS. And for my portion of the presentation, I wanted to speak a little bit about some of the changes we've made in recent months to accommodate and support the feature that Lars introduced into upstream Git. But before we dive in, I want to sort of illustrate a little bit of the timeline of things that have gone on so far. So towards the end of October of last year, Junio merged Lars's filter process branch into the next branch of Git. And we know that towards the end of November, Git 2.11 is scheduled to be released. So this just gives us at LFS over 1 month or so to implement support for the new process filter before 2.11 is released. And our main objective is to release a new version with this support before 2.11 so that users can upgrade LFS as they please. And as soon as they update Git, the time that it takes to check out a branch will decrease without any sort of additional configuration. So now that we have a time frame sort of centered around what we need to build in LFS, I want to take a quick look at the actual feature we're hoping to provide to users. We want a user to be able to check out a branch and then be on that branch. But under the hood, there's a lot more going on. If you rerun this command with the trace packet flag, you can see that first Git sends us a bunch of data, and then LFS needs to respond with a corresponding set of data before they'll actually be on the branch. So to get this going, Lars kicked things off with a work-in-progress kind of spike pull request. And there are a few important attributes that I think made this pull request particularly successful as a starting point in building this new feature from scratch. The first is that it was published as a work in progress. The code that was provided, of course, worked, but there were still some kind of open questions that needed to be answered about exactly how the code should be implemented and what those interfaces should look like. This is a particularly good approach to getting started off with working with pull requests, since it affords us the opportunity to get something working without getting caught up in the implementation details up front. The second detail is that Lars stated that he was open to a thorough review of his code. Lars isn't a Go expert, nor am I a C expert, so we leveraged our respective areas of expertise to allow us to work quickly in the areas that we knew best, while making the other parts of the project that were less familiar easier to deal with. And the third is that the pull request was relatively small in size. This allowed Lars to pretty quickly validate that the idea would actually work within Git LFS, and we could get to discussing the remaining implementation questions with a rough sketch of everything already in place, instead of working through those questions up at the start. So to recap, when starting on a new feature from scratch, start small. This will afford you a few key benefits when making the rest of the feature. First, by not worrying about the implementation up front, you're able to answer a very important question, whether or not that feature is actually going to work. By validating the feature that it'll actually work, you've by necessity implemented it. The implementation may not be perfect, but it's there. So instead of worrying about it up front, you can come back to it as you please and refine it along the way. And that's exactly what we did when taking Lars's Spike branch to a release, is I identified sort of 5 key steps that we would need to take, and then we implemented each of those as a pull request, merging back into his until we were eventually ready to cut this as a release. The first step of things that we needed to do was create a series of integration tests to verify the most basic behavior. And this change sort of came in two parts. One was explicit, and the other much more implicit. The explicit test was small. Create a repository with LFS enabled, have 2 branches with 1 file on each branch, switch between the 2 branches, and make sure that the files were there and had the correct contents. The implicit change, however, was much larger, is that we ran the entire process, the entire integration suite, through the new process filter to verify that all of our existing features and assumptions wouldn't break with these new changes. Once that was done, we could get to refining the packet line implementation that Lars provided in his original pull request. Now, for those unaware, packet line is an encoding format that Git uses to send data between itself, as well as to external processes like Git LFS. Lars provided an initial implementation of this protocol in Go, but there were a few things that I wanted to go in and refine before we could use the code elsewhere. This was the pull request that did that, and it was fairly uninteresting. Some light refactoring, some easier testing, and it made the following steps kind of much more fluid. So once we had a solid base to start with at the kind of most basic level of packets, we could start implementing higher level APIs that would be able to understand and answer some of the questions that Git would ask us in the process filter communication. Now, to implement this, we chose the scanner pattern, which is common in many languages, but particularly in Go, this worked great for our use case. The scanner allows us to consume data in a sequential loop, which matches perfectly the way that Git sends data from itself to LFS. So here's a little bit of an example of how it works. In a loop, we call the scan method, which returns true when there's more data to process, or false when there's an error or we're at the end of the stream. So while we have data to process, we grab the next request that Git sent us, decide based on the command that Git told us to do what we should actually do, whether that's cleaning, smudging, or doing something that we don't know about. And then once we're done, clean up any errors and respond as appropriate. And really, at the highest level, that's about it. That's all that's needed to kind of make the most basic decisions about what we should do according to what Git said. But there's a problem with this implementation, is that the header type that we were returning back included this payload field. Now, specifically, what's wrong with the payload field is that you'll notice it's a byte array, or a slice of bytes. Now, this is fine when we're converting from pointer files to large objects, because the data of the pointer files is relatively small and can be sent and stored in memory, buffered up front. However, for converting the other way around, for large files down to pointers, these files often exceed the available memory on your computer, so they can't be buffered all up once at front. So what we need is sort of a way to deal with this chunked data that Git is sending us in a stream-like fashion. So that kind of kicked off the next and remaining 2 series of PRs that was packet line-based I/O. So the first thing that we did was we provided an I/O reader implementation. Now, for those that are unaware, the I/O reader interface in Go, which is a part of the standard library, looks like this. It has one method called read, which takes in a byte buffer p, which you can read from an underlying data source into, and it returns n, the number of bytes that it read, as well as any error that it might have encountered along the way. Now, if you remember from a previous pull request, we have this great interface for reading packets from Git. So we can combine those two and define a packet line-based reader that we can consume data in a stream-like format that's backed by this underlying protocol from Git. So we create this type and implement the interface by defining the read method as shown before. And in a loop, we grab the next packet that was sent to us from Git, returning any error if there was one, copy that packet's data into the buffer that we're reading, and then at the end, return the number of bytes that we read. Now, of course, there's some more detail that I'm omitting here, like how to deal with overfilling and underfilling these buffers, but this is the general kind of sense of it. And by implementing this type, it allows us to treat this chunked data stream as coming from Git in the same way that you would treat a continuous stream of data. This removes the constraint that we have to read all of the data for a particular file up front, but it also provides us with some additional benefits. One of the things that you can imagine that LFS might need to do is calculate the SHA-256, the signature of the contents that's being sent into it for these large files. So we can use the scanner pattern from before, grabbing the request from Git, calculate a signature object, which will read in data and recalculate the stream or the signature as appropriate. And the nice thing about this type is that it can accept any amount of data up at once. So we can use small buffers of about 500 bytes and not buffer the entire data up front. We then copy from the request body, which is the file's contents, into the signature calculation. And what's great about this is we're kind of converting between a couple of different mediums. We're going from the packet line protocol up to the raw bytes and then down back into the signature. And all of this is sort of transparently abstracted behind this one line of code. And once we're done with that, we can ask the signature for the sum, and it'll print out the SHA-256 of that file. The last step and sort of natural complement to this reader was an I/O writer. And this is the pull request that implemented it. The interface is fairly similar. It contains one method, write, that has the same signature, but the behavior is, of course, a little bit different. Instead of reading into P, you read out of P and into the underlying data stream, returning n the number of bytes that you wrote and any error if you encountered one. And again, this is an interface, so you can write to many things like files or network sockets, or in our case, Git. So we define the packet line writer type and implement the I/O writer interface by defining the write method. We keep track of the number of bytes that we've written so far, and so long as that is less than the total number of bytes in the payload that we wanted to write, we grab the biggest amount of data that we can write without exceeding the maximum length of a packet, write that packet, returning any error if we encountered one, increment the number of bytes that we wrote, and then at the end, return that. And again, there's of course some simplifications that I'm making here, like one of the attributes of this protocol is that you should write the biggest packet that you can. So we have to accumulate data and buffer it internally up to the maximum packet size before writing it out. But again, this is the basic gist of it. And like the reader, it provides us with some additional benefits. One of the functions you can imagine LFS implementing is a smudge operation to, given the OID or SHA-256 of a file's contents and a destination to write that large file to, write the large file. So given the OID and the I/O writer, which is going to be in our case backed by the Git packet line protocol, we can grab the local path on disk where the cache of our object remains, and that's in your .git directory. We can open the file at that path to get a reading handle on that file, returning any error if we encountered one, and then transparently copy from the file down into the packet line protocol. And again, we're sort of moving through a few layers of strata here. We're going from the packet line protocol to the raw bytes and then down into the file system, again, all in one line and without having to worry about it. And really, that's about it. So once we had sort of covered everything for this spike pull request, we started testing. And we found a few bugs, and we fixed them, and we eventually turned this into a release. We presented the LFS 1.5.0 release ahead of schedule and right before Git 2.11, which meant that people could upgrade LFS as they wanted, and as soon as 2.11 was released, their repository checkout times would instantly improve. And as we benchmarked this release against the release candidates for Git, we found that this made checkout times on branches using LFS about 80 times faster. Now this, of course, varies on a few different attributes of your repository, like how many files you have on the average size of them. But in general, about 80 times faster, and that's fantastic. Going forward, we're still looking at a number of ways to continue improving upon these changes that we've made in Git and Git LFS. One thing that we'd like to do is, instead of responding with the entire contents of a file, respond instead with a promise. Now, Git checkouts are fast right now when we have the data already in the cache, because we can just copy it and stream it right back out to Git. But the problem comes when you're doing, say, a clone or a fetch, and we're downloading lots of new files from the remote. The problem here is that if we don't have the file cached, we have to download it completely, send that data out to Git, and then have Git acknowledge us before we can even know about the next file. So that leaves a lot of this internet bandwidth underutilized, and we can do better than that. So what we'd like to have Git be able to do is say, LFS, please write this file, and LFS would respond with, I don't have that file yet, but I'll get it, I'll download it, I'll put it in this temporary directory, and then you can exchange it into the working tree when I'm ready. And the great thing about this is it's already a discussion on the mailing list, and we're hoping to have it in Git and Git LFS fairly soon. One other thing that we'd like to explore is, instead of chunking and streaming these data, these payloads through the pipe, exchanging temporary paths on disk. And we know that in pipes on Unix and OS X are fast, but on Windows, the abstraction makes it much slower. So while the improvement in checkout speed on Mac was about 80 times, on Windows, it's only about 57 to 65. So we're exploring whether or not sending just files instead of this data over a pipe might be a little bit faster. And beyond that, we don't know. This is just the start of this feature, and we're still continually discussing ways that we can profile and figure out how to make this even faster in the future. Taking a step back, working with Lars on this feature was such a pleasure. We were able to work across 2 different organizations between AutoDesk and GitHub to impact both projects, LFS and Git, and leverage our kind of relative areas of expertise to make a contribution that will impact developers using both projects. And I think that's why Git and source control and sites like GitHub and GitLab and Bitbucket are so important, is that they facilitate these types of interactions. And I can't wait to continue to make this improvement, and I'm so excited that I get to be here with you, where you make these types of improvements every day. So with that, thank you very much.